Welcome. Now we're going to talk about substitution in multiple integrals. And substitution is a way of changing variables by applying some sort of transformation. Okay, so these are ideas with coordinate transformations, which are used to evaluate multiple integrals by substitution. So it's kind of like a W substitution in a sense. So the idea of what we're doing is, say we have some UV plane and we've got some surface in the UV plane. We'll call that G, and any ordered pair in there would be U comma V. The idea is that we are going to apply some transformation. We'll call that T. And in that transformation, X might be some function G of UV, and Y might be H of UV. So that transforms it over to the XY plane. And we have a surface now R. And a point in there might be XY. And then, of course, we can go in the opposite direction. That would be T inverse. So we're taking something, we might call this the pre-image, and we are converting it to a Cartesian XY plane, which is our image. And then we can go back to the pre-image. So both of these are in XY planes. I just can't use XY twice when we talk about that conversion. And I think one of the better ways for us to understand what's going on here will be to jump right into an example. So for this example, we're going to let T be some transformation from the UV plane to the XY plane, and it is defined by the following. We have that X is 1/4 of the quantity U plus V, and Y equals 1/2 the quantity U minus V. So the first thing we're going to do a couple of different things to kind of help us understand this. So given some ordered pair 1, 3, let's apply the transformation T. So essentially, we're being asked to find T applied to 1, 3. So what does that equal? Well, I can take 1 and 3, plug it in here, I get 4. 4 over 4 gives me 1. And I can say 1 minus 3, negative 2. Negative 2 over 2 gives me negative 1. So I had a point in the UV plane, and then I transformed it to some different point at a different location in the XY plane. All right, so the next thing we're going to do is we're going to think about visualizing this. So we're going to sketch the image under this transformation that is bounded by U between negative 2 and 2, and V between negative 2 and 2. So we're going to visualize this in both planes. So my pre-image G is bounded by this domain and range, if you will. So what does that look like? That is 2 on the U-axis, 2 up and down on the V-axis, and the pre-image here this represents my G, my pre-image. And what we're going to do is we're going to apply some transformations. We're going to apply the transformations provided up here, what we know about X and Y, to create some space R in the XY plane. Now, in order to do this, we have to sketch several UV curves. And again, you're not going to be doing this all the time, but I think this helps you visualize what's going on here. So in order to do this, I'm going to take both of these and I'm going to solve for U and V. So I'll have 4x and 2y. All right, so what does that give us? Here's my system. Call this part I. 1. We have 4x equals U plus V. 2y equals U minus V. So if I were to add these together, I would get that 4x plus 2y, 4x plus 2y equals 2u plus 0v. So 4x plus 2y equals 2u. Another way we could think about that, taking those same equations, 4x equals u plus v and 2y equals u minus v. Now, if I were to subtract this, I would get a different equation. My u's would cancel, and I would have 4x minus 2y equals no u, and then we would have positive or plus 2v. Now, both of these equations, I can divide them by 2. So dividing this first one by 2, I have 2x plus y equals u. And then the second one by 2, I've got 2x minus y equals v. And all we've done here is to solve a system of equations. We had to get a little creative to do it. But now we have u in terms of x and y and v in terms of x and y. And we're going to use those because we have bounds for u and bounds for v. So let's think about how this helps us. So let's deal with u. So a couple things that we know about u. U is between -2 and +2. And u equals 2x plus y. So what does that give us if I plug these values in? You know, I'll be able to develop some linear equations. So if I plug in -2 here, I have -2 equals 2x plus y, or rather y equals -2 minus 2x, which I've now written there. And we could plug in -1. -1 equals 2x plus y. That's going to give me, if I erase that, we have y equals -2x minus 1. And you'll start to see a pattern here. We'll get y equals -2x, y equals -2x plus 1, and y equals -2x plus 2. So I kind of shortcutted that work for us because it's pretty repetitive, but you start to see a pattern. If I plug all of these values of u in and then I isolate y, I get all of these linear equations. So now I'm going to do the same thing for v. So I've got my v values. Again, v was between -2. We can list as many values as we want. -1, 0, 1, and 2. I'm just listing the integers between -2 and 2. And really, if I went ahead and isolated y here, I'd move that y over, subtract the v. That's the same as y equals 2x minus v. So I've got y equals 2x minus -2 is plus 2, y equals positive 2x plus 1, y equals 2x, y equals 2x minus 1, and y equals 2x minus 2. And so we're really going to focus on these outer bounds, u equals positive 2 and 2, and the same for v, v equals positive 2, and v equals -2. So I cleaned up my page a little bit, and just to help us remember what we're doing is I'm taking this image on u and v, and I'm transforming it onto the xy plane using these lines that we have just found. So what does that look like in my xy plane? Okay, go ahead and mark that out for us. So this creates a region. These lines bound a region. So this first line right here, -2x minus 2, that's a slope of -2 crossing through -2. So I've got a line that looks roughly like this. And y equals -2x plus 2, that has the same slope of -2, but passes through y equals positive 2. Over here, y equals positive 2x plus 2, so we've got a slope of positive 2 passing through the y-intercept of positive 2. And then y equals 2x minus 2. And what you can see is all 4 of these lines bound kind of a diamond region here. This is what we call our R. So that's our transformation that we applied created this new region R in the XY plane. And so what you notice here is that both sets of bounds change. So it's essentially kind of like two U substitutions, right? The bounds change over both of the integrations. So we have two integrals. Either way we do it, right? We'd be splitting it up. If we were going it this way, we would have to break that into two different sets of bounds. Or if we were going horizontally again, we would have to break that into two sets of bounds. So it doesn't matter if we choose dx, dy when we think about integrating, or dy, dx, it's still going to have two integrals. So what we're going to be doing in this section is we're going to use transforms to create a pre-image, because the pre-image, this is our image here, and the pre-image would have been much easier to integrate. So we might go from XY and create some UV. Now, this was a rather long and tedious process for us to do. So in the next video, which you'll meet with me in a couple of seconds, we're going to start talking about the Jacobian just a little bit. I'm going to mention it to you, and then we will define the Jacobian and we'll show how that can simplify our calculations a little bit.